So now that you have seen many kernels, so many different representation, the thing now is with this plethora of different representation, different kernel, how can I choose the ones that is the best? Okay? Is it possible to learn this representation from data? This would be great. Okay? So the question of this last part of the talk will be why not to try to learn the kernel matrix or the kernel function. Okay? So we see very very fast way, we see parametric methods for kernel learning, transductive feature extraction with nonlinear kernels, Specter kernel learning, and we give just an introduction to multiple kernel learning, which will be the focus on the last part of this talk. Okay, so the first kind of methods that are used for learning a kernel using data is basically by parameterizing one kernel, like in this case. So basically you are generalizing the RBF kernel in this way by putting this matrix M and then trying to learn the parameters, the entries of this matrix M, which is a semi-definite matrix, and then to learn the kernel that, for example, maximizes the margin in the training set, for example. Okay? So in this M, you can also give some constraints to this M. For example, in the basic case, this M will be of this form. And you can recognize that this form is exactly the radius basis function kernel, where gamma is now beta 0. Okay? But also you can just say that M is an diagonal form. So you have, in this case, you have n parameters, where n is the number of examples. Okay? And you can call this version anisotropic radius basis function, because you have, for each dimension, has a different parameter to tune. Okay? So the idea of kernel learning in this case is to learn these coefficients in a way to optimize some criterion. For example, to maximize the SVM margin. Okay? So this is the idea. Another kind of approaches that are currently used are the ones that perform a kind of a feature extraction from implicitly in feature space. For example, kernel principal component analysis. Maybe some of you may recognize the principal component analysis to be one of the most popular kernel, one of the most popular methods to for feature extraction for linear data. Okay, but you can use the same method in feature space. Okay, so by computing the so-called principal components and the projection on these principal components in feature space. Okay, and also in this case, the kernel trick is used. Okay, one big issue of these kind of methods are that this is actually a transductive approach. What transductive means? What does transductive mean? It means that, in fact, since you compute this method works on the kernel matrix and not on the kernel function, then when you have new unseen data, you cannot generalize, you cannot compute, you don't have the values of the kernel matrix, of the kernel between this new data and the ones that we had in the training set. So the solution of these issues has been proposed, and the one that seems to work the best is are techniques based on outsample techniques that are used to approximate the value of the kernel based on the kernel that are computed on the training data, with respect to the training data. Okay? Another kind of approaches are the spectral kernel learning. There is a property of positive definite matrix that says that basically one matrix K, positive definite matrix, can always be seen as a combination of rank 1 matrices obtained using the eigenvectors and weighted by the eigenvalue lambdas. Okay? So basically you can reconstruct your matrix K using the eigenvectors of K and the eigenvalues. Okay? So the idea here is using is to use transformation of these eigenvalues, for example, with a function tau, lambda, and in this way you can act implicitly on the representation in feature space. Okay? Similarly to the previous approach, also in this case you have the problem that in fact this is a transductive approach. So it's not easily generalizable to new data. Okay? Finally, the multiple kernel learning. Basically, in this case, you have a bunch of kernels. We call these base kernels or weak kernels, and you want to compute a positive combination of these kernels in order to get a new kernel, a combined kernel, which performs better on your data. Okay? And I think you recall that when this combination is positive, you know that the combined kernel will always be a valid kernel. You remember the sum of kernels is a valid kernel. The multiplication of a kernel by a scalar which is positive is a valid kernel. Okay? So basically any positive combination of kernels, matrices, of kernel functions is a valid kernel. So this is a very general way to build new kernel based on existing ones. Okay? There are many different methods. The simplest one are fixed methods, for example, by just taking the average of the kernels. This is a very naive way. Or maybe to choose these weights based on the accuracy of, for example, the SVM when used with that individual kernel, and so on. There are many heuristics that can be used for setting the weights, the coefficient there. But also there are methods which plug the optimization of the coefficients eta into the formulation of the original problem, to the SVM, for example. Okay? And just to compute, for example, the combination that is able, then the new representation that is able to maximize as much as possible the margin in feature space. Okay? Okay. So there are questions? This part?
The question is a suggestion from you. Which one of the techniques you would suggest?
We will see in the following, but I'm currently using this kind of methods, clearly, where we are able to optimize together the parameter of the SVM and these coefficients in order to obtain, we'll see, big margins or minimize the ratio, the radius margin ratio.
But then KER, the kernel, are indexed as a function of power. Are they all the same kernel that you are combining, or you are combining kernels of different types?
No, you can combine kernels of different types. Yes, yes. For example, you can combine conjunctive kernels of different degrees, or you can combine RBF with different gammas, and so on.
And there is some hard, you need some hard, some understanding of the problem.
Yes, yes, sure. But we will see some results about the expressiveness that motivate the use of particular kernels, because they are very, very general. It can be used as a brick to build very complex kernels. Is the topic of the last part of the talk. So there are other questions? Any other? It's a little bit too late. So I'll try to go fast in the last part. If you have any point that you want to me explain further, just ask, okay? Okay, so the topic that we approach in this last part of the talk is how you can generate hierarchical representation. So basically the idea is to create representation with different levels of expressiveness, and then to combine these levels of representation. And you do this by using multiple kernel learning. Okay? So when you look at the some priors to get a good representation, you can see different aspects of the problem. For example, you can ask to have a smooth function. This is a good prior for the solution of your problem. Or you can look at multiple explanatory factors, or to find a manifold in your data, or look for sparse solution instead of non-sparse ones, or to look for some hierarchy on your explanatory factors. This is exactly what the deep architecture are trying to do. Okay, deep architecture basically generate models with several levels of abstraction. So with representations that have different level of abstraction, and then these are the state of the art in many different tasks nowadays. Okay? In particular, the deep neural networks are becoming very popular now. Okay? Anyway, they have some drawbacks. Okay? For example, it's not clear how the decoupling between the representation and the model generation. Okay? It's not so clear. Also, typically, they require high training time, because when you go more than tens of layers, it's very difficult to handle this kind of networks. And generally, you can find very easily, you can converge to suboptimal solutions, because there are many local minimum in your problem, and there are the so-called vanishing gradient effect. It means that when you use in a neural network a set of layers, and you use, for example, the backpropagation algorithms, it happens that the gradient that you compute to apply the backpropagation is vanishing in the very first levels. So basically, you cannot perform training, basically. Okay? So instead, we consider a different approach, which is based on kernels. Okay? In particular, the multiple kernel learning that we have seen. And you can see also that when you apply a multiple kernel learning algorithm, basically you are doing something like this, because you are looking for this coefficient AR, and it's possible to demonstrate, to show that this corresponds to have a new representation where all the representation phi1, phi-r are now replaced by, now reweighted by these coefficients. Okay? So basically you are changing the representation by concatenating all these feature spaces and weighting different ways the different parts. Okay? So the idea here in this part is to define this part of this vector in a way that the expressiveness, the complexity to have this representation of increasing complexity, and to find the right tuning of this complexity. Okay? For this, we have to define the so-called expressiveness of kernels. Basically, the expressiveness is something like the notion of VC dimension that we've seen before. Basically, the expressiveness of a kernel can be thought of as the number of dichotomies that can be realized by a linear separator when you use this kind of representation. And it's possible to see that the rank of the matrices that are computed using this kernel is related to this quantity. Okay? For example, you can show that if a matrix, kernel matrix K, has rank equal to rank K, then there exists at least one subset of examples that can be shattered, one subset of examples of size rank K, that can be shattered by a linear function. So, if you have rank 5, it means that there are at least 5 points in your set that can be shattered, linearly shattered, okay? By an hyperplane. This can be shown. But obviously, using the rank is not so easy, because to compute the rank, you need to decompose the matrix. Okay? So we proposed a different measure of the complexity, which is called Specter ratio. Basically, the Specter ratio is the ratio between the one norm and the two norm of the eigenvalues of the kernel matrix. Okay? But the one norm of a semi-definite matrix can be just computed using the trace of the matrix. It means the sum of the entries in the diagonal. Okay? While the two norm of the eigenvalues can be computed by using the Frobenius norm of the matrix. Okay? So basically, this ratio represents an approximation of the rank. And why this is the case? Because you can show that this ratio is always less than the square root of the rank, and it's always greater than 1. In particular, if you take the identity matrix, which is the most complex kernel matrix, because the most expressive kernel matrix, because basically the identity matrix is a kernel matrix that always says everything is different from everything else. It's only similar to itself. Okay? So it's the most irregular kernel matrix that you can think of. Okay? So in the case of the identity matrix, you have the maximum Specter ratio, which corresponds to square root of L. The L are the number of examples. Okay? So the maximum rank that's possible to obtain. Okay? In this case, you have all possible 2 to the L, dichotomies you can realize. Okay? When the kernel is the constant kernel, it means all the entries are the same, and they are positive, obviously. In this case, you have the minimum Specter ratio, because it means that everything is similar to everything else. Okay? So in this case, you have the minimum Specter ratio. And another interesting property of this measure is that if you multiply with a positive scalar, this measure is invariant to multiplication with a positive scalar. It means that if you multiply with alpha, which is a positive scalar, you obtain the same value. Okay? The value doesn't change. Okay? So this is a good property, because you can see that, for example, in SVM, if you take a kernel matrix K, or if you use a kernel with a weighted version, the results are basically the same. Okay? Doesn't change the solution of the SVM. Okay? So basically, we can define a relation of generality between different representations. In particular, given two kernel functions, ki, kj, we say that ki is more general than kj whenever, for any possible dataset x, we have that the Specter ratio of the matrix evaluated on data on X using the kernel matrix I is always less than the Specter ratio obtained for the matrix Kxj evaluated on data X using the kernel J. Okay? This should be true for every possible data set X. Okay? And after that, the big picture of the proposed algorithm is in the following. We construct a hierarchy of kernels of decreasing generality, of increasing specificity, expressiveness, and with this, we apply a multiple kernel learning algorithm on these R+1 kernels. Okay? So computing the weights of the combination and using these weights to compute the final multiple kernel learning kernel. Okay? So here there are many degrees of freedom. For example, the choice of the multiple kernel algorithm you choose here, and how you decide which kernel to use here. Okay? So there are many different algorithms, and the algorithm basically can be divided in two families. The first family is the margin optimization family. In this case, basically you have algorithm that can optimize the margin that you obtain for your SVM. Okay? And in the other case, you optimize together the margin and the radius, the diameter of the minimum enclosing ball together. So by optimizing directly the ratio. There are two main approaches. One is the Du et al., which are the authors of this work, which optimizes an upper bound of the radius margin. Actually, it optimizes this upper bound. Okay, and the other one, which is ours, is RMGD, which is able to optimize the exact ratio between the radius and the margin. Okay, we'll see something afterwards. Okay, and the EasyMKL is another algorithm. I think I don't have time to go into the details of this algorithm, but the last thing I want to say is that there is a family of kernels which are called dot product kernels, which include polynomial, radial basis function, rational quadratic, Cauchy kernels, many of these, which is defined like this. One kernel is said to be a dot product kernel when the kernel can be formulated based on the dot product kernel of the original vector. For example, in the polynomial case, you see that the kernel between x and z is equal to the dot product between x and z plus c to the d. So this is a function of the dot product. Okay? So this is why this is called dot product kernels. Okay? And there is a very important theorem in analysis that says that all these functions, the function of this type, can always be seen as a combination, as a positive combinations of basically homogeneous polynomial kernel like this. Okay, so basically in our case, you can for each of these kernels, you can compute the corresponding Maclaurin expansions and computing these weights A. Okay, so basically there is these results that says that for any dot product kernel exists what we call the dot product polynomials like these, with opportune coefficients A. Okay? And similarly, if you have any of these are a dot product kernels. Okay? And this you can see different dot product polynomials coefficients for any S. For example, for RBF, you can see you have a situation like this. For different S, you have a weight that follows more or less a Gaussian. Okay? Now, in the case of homogeneous polynomial kernel, it means when C equal to 0 here, you can show that basically you have a kind of dependencies between the features in the polynomial embedding. In the polynomial embedding, when you map using the linear kernel, basically you have these features. When you use the 2 degree, then you have this kind of features. So you have basically multiplication of pairs of variables. For 3, you have similar thing, and so on. So you have a kind of dependencies between the values of these features. And this dependence gives an important result with respect to the generality. And we can show that, we can demonstrate that when S, if you use S plus 1 instead of S, you get a more specific kernel. I mean, if you increase the degree, you lose in generality. So you get more complex kernels, okay? Even more complex kernels. So our idea is basically the following. You take this combination, and you know that this is, usually this is parameterized, and you can obtain different dot product kernels. So our idea is, why not to learn this coefficient using multiple kernel learning? So basically we generalize, we can build any possible dot product kernel using data, learning from data, okay? So we are trying to learn the representation on the space of dot product kernels using data. This is the idea. Okay? So this is this algorithm. And another important results we obtain is that the same reasoning can be applied to Booleans. In case of Booleans, we have stronger results. When you have Boolean vectors, then you have similar results, but involving conjunctive kernels. So basically, any dot product kernels defined on Boolean vectors can be defined as a combination of positive weights and conjunctive kernels of increasing arity. Okay? So in the second set of experiments, we have tried to apply the same algorithm, but using this version. So we try to use in Boolean, when coping with Boolean vectors, we're trying to learn non-parametrically these weights given the individual conjunctive kernels, base kernels. Okay? We apply the same idea as before for dot product kernels for standard vectors.
What is the meaning of the tilde?
The tilde is the normalization. Okay. So basically, we can show that any homogeneous polynomial can be seen as a combination of conjunctive kernel. And also, any conjunctive kernels can be seen as a positive combination of normalized conjunctive kernels. So basically, in this case, we have these kernels are all normalized, and you want to learn these parameters, which are basically the parameters of the dot product kernel.
Why you change the name from H to G?
Because they are different. These values
Correspond to non-normalized.
exactly. This is the way. The results that we have demonstrated is that if you have any homogeneous polynomial of degree d, you can see this in the form of a sum of a combination of conjunctive kernels of degree s for increasing s. Okay, from 0 to d. Okay, but then you can see any dot product kernel f in the form of a sum with s from 0 to m, which m is the number of values 1 in the variables, of this value as the coefficient. Okay, but these values is not the same of h, clearly, because this is the coefficient that you need to form the dot product kernel. Okay, while this is the coefficient that you need to form the homogeneous polynomial kernel, which is just one part of the homogeneous polynomial kernel is this part of degree d of degree s is this part. Okay, after that you have these parameters that you can put everything inside and obtain this g that summarizes all the coefficients that accumulate together. Okay, so basically you have everything of this form. These are kind of results where for different data sets we take just a sample of the data set, and basically you can see that EasyMKL is generally better than using the simple average, which nevertheless it's a very good baseline. It seems strange, but just taking the average of the kernel, it means just taking the combination weights equal, it's a good baseline in general. Okay, but EasyMKL, that is a margin maximization optimization algorithm, is able to perform generally better than just taking the average. But here you can see also the ratio that you obtain in different when different algorithms have been used. And you obviously, as would be expected, in the case of RMZD, I remind that this is the method that optimizes the ratio. Does it try to minimize the ratio between the radius of the minimum enclosing ball and the margin? And you can see that minimizing the ratio implies that also the accuracy is greater, is good. Okay? It's better than just maximizing the margin. And this is the final message. I mean, in the case of SVM, it's correct to maximize the margin because you are keeping the representation fixed. But when you want to change the representation, then the diameter, the radius of the minimum enclosing ball is not constant anymore. Then you need to optimize something more like the ratio, which which involved the radius of the points together with the margin. Okay. And another interesting features that you have noticed using margin-based algorithms and radius margin ratio based algorithms is that using the radius margin ratio based algorithms, in general, we get more sparse solutions. So basically only few kernels are selected in the combination, like here. You can see the number 3 get very high values, very high coefficients, like 0.5, while the other very low values. Okay? This is not the case in the, for EasyMKL, which is a margin-based algorithm. In the case of margin optimization for multiple kernel learning algorithms, we observe a distribution of the weights that is more like the uniform. Okay, so the one that is returned by the average. So I think I finished my talk. I hope it's good. 6 o'clock.
Can live with that. Yeah, but the talk was good, so.
Okay.
Yeah,
do you have any questions?
I have a general question, curiosity. I don't know.
At the beginning of the last part, you said that this method can be also similar to the neural network, deep neural networks.
Yeah, in the sense that when you apply deep neural networks, you basically use many levels with different level of abstraction. Okay, so the first level, basically you consider raw data, and after that you try to construct features which are more general, okay, in a less expressive in itself, but catching what you really need. I don't know how to explain better. In this sense, you have, in our case, we have this situation. Where is the... In our case, we have this situation. This situation in which you can imagine this as the levels. So the multiple kernel learning basically define different representations. For example, the representation of the linear kernel. After that, the representations of homogeneous kernel, polynomial kernel of degree 2, homogeneous polynomial kernel of degree 3, homogeneous polynomial kernel of degree 4, and then we find the combination. Instead, in the deep neural network, they usually use only the last level, the very last level, okay? In our case, we just combine all these representations. This is the, yeah. I don't know if...
Yeah, and also about the convergence time of this kind of, is really high, or?
No, not really, because in this case, in the case of EasyMKL, it's very simple. The algorithm is very simple, and it requires a time which is only linear with the number of kernels that we use. Only linear. A constant in memory. So there is a very high scalability with respect to other methods, which are generally
because it seems
are
like
not
that
so.
this is a powerful method, so I cannot understand the popularity of deep neural network against this kernel method.
No, they are different in many aspects. It means that the popularity of deep neural network is that basically you define methods to extract new feature from your data. Okay, in this case you are extracting new features, but you decide which kind of features you want to extract.
Okay.
So in this case, you decide that you want to extract all the polynomial features, for example, and you want to combine this kind of polynomial feature to have a better representation. In the case of deep neural networks, instead you have algorithms that optimize with respect to other criteria and try to find a representation, typically in an unsupervised way, to find the representation that fits the more your data. So the approaches are quite different, but the idea of hierarchical representation is the same in this sense.
Yeah, thank you.
Any more questions?
Yep.
Yeah.
Question about the last figure, the last slide, please. Yeah, can you stress more the reason why the result that are related with the easy NKL looks like flat, you know? The easy NKL, so the white.
Yes,
the
but
white bars.
these are the weights, okay? The combination weights.
The combination weights.
Yeah, it's a good question because we don't have the answer. We observed this behavior in a large majority of the data sets we tried on. It means 14 or something, many of those. In almost always, the behavior was something like this. I don't have the answer, the real answer to this question.
Okay.
But we are working on this. We are working on this and trying to understand why this is the case.
You guys have any other questions? No? Because I imagine flatness may imply the fact that they have the same importance, right? So that is what is striking, what is strange.
Sorry?
So this flatness,
Okay.
the reason why I find this question interesting is that it may imply that they have the same importance.
All the kernels get the same
That
importance.
sounds strange. In that case, I would be tempted to use the kernel with the smallest number of parameters, right?
Okay.
Which is expected to generalize better.
The smallest number.
Of parameters.
Okay.
Yeah.
Yes, this is a difficult question because in reality, the role of the combination is not to select the best kernel. So I'm not sure that giving the same weights to all the kernels means that all the kernels have the same importance.
Okay.
I'm not sure that, because giving the same weights, it means that you want a representation that that considers all these all the individual representation the same way.
Okay.
But I'm not sure you can say that you are giving kind of importance of one kernel or another.
Okay. They may be all important, but you need to consider them in the same amount.
Exactly.
For different degrees.
Yes, yes.
But here, as a matter of fact, when you see that they are sparse, you're saying I can just pick 2 kernels instead of picking 10. This is what you said before.
Yeah.
So this is basically implicitly you're telling me. For me, I associate this weight with an importance.
Yes. One thing we can say, maybe to answer the student there, is that basically if you try to minimize the radius, basically considering too many kernel, in some sense it's increasing your the dimensionality of your representation. So basically it's spreading your data. Okay, so when you use a high number of kernels, basically you are increasing the radius of your data. So if you want to keep your data in a small radius, you need to focus more on few kernels. This is the first answer I feel, but I'm not sure this is the correct one.
And as a last question from me, because I think it's very important. You mentioned deep neural network, and you associated this term with suboptimal learning.
Okay. Suboptimal.
Yeah. And now I would like to understand, or maybe if you have an answer for that. With SVM, you're supposed to be closer to optimal?
In this case, we almost always have optimization problems which are convex, exactly, or very, very close to convex problems. Exactly. This is the major difference with deep architectures, which are not convex at all. Exactly. They have a lot of local minima, and the only thing you can do is to repeat the optimization multiple times and to find different local minima and find the best.
You guys get this point? So, because in SVM are formulated, you find the margin, you find the solution. It's formulating a convex problem. Although we haven't seen that today, right?
Yeah.
So that is also the power of this technique.
Yeah. This kind of problems. Yes.
That's taken into account. In fact, this is why someone in the community, the kernel community, says this will, in the future, these techniques will ultimately be better than neural network. And we can replace neural network with this kernel.
Even if now with deep neural network, people are starting to say, yes, but the convexity is not so important.
So there is a debate, ongoing debate.
Maybe it's fashion.
Yeah. Okay. Thank you so much.
Thank you very much. Thank you for your attention.